Today we're going to finish section 1.2 where we were constructing models to solve problems. We had looked at some basic problem solving strategy ideas last time and some formulas. I think we had done just really one example of actual problem solving, and it looked like this. We talked about interest or payments, that kind of stuff, and about how $5 may not sound like a lot, but if you're only borrowing it for if you're paying $5 for just a month's worth of time, the percentage actually ends up being quite a large percentage rate on this particular problem. All right, so one reminder before we get too far into the process here is that we didn't finish this last time, so it won't be due this evening. It will be due on Friday evening at midnight. So unless you want to spend your Friday evening doing it, I would encourage you to go ahead and start working on it, even if it's not due until Friday at midnight. We should also finish or nearly finish 1.3. So on Friday, you will have a quiz. We will finish 1.3 one way or another. You will have a quiz over 1.2 and 1.3. So again, if you haven't already done so, you should be working on the homework, the written homework for sections 1.1, 1.2, and 1.3. So that's coming up. All right, new example. This one's about temperature. If the temperature at 11 p.m. on New Year's Eve in Times Square was 23 degrees Fahrenheit, what is the temperature in degrees Celsius? Yes, Holly?
What's written homework?
Written homework, there's a list of problems inside of middle rooms that come straight from your textbook. And then the textbook pages are actually located inside of My Math Lab. You can print them off. And then when you bring those in on Friday, you'll take a quiz. And the quiz is simply a copy from one paper, paste to the other paper if you actually have done the homework problems before you show up.
My lab, not Pearson, my lab and mastering?
It's the same thing, hun. Yeah, My Math Lab, Pearson, all that stuff's the same location. It's just the company name versus the product name. Yeah, it's like Kleenex versus tissues. Moodle Room's got the list of the problems. And then My Math Lab actually has your textbook problems. It's underneath course content. There's several ways to locate it, but course content's kind of their catchphrase for textbook instead of there. I wish it said textbook, but it just doesn't, so yeah. All right, we had a formula last time. It was on that list of formulas that related Celsius and Fahrenheit. There's actually a couple formulas. I gave you one of the two. Which one did I give you? Do you guys remember? Did it start out with Celsius equals like this? Okay, and then you said 5/9. Keep going, what was next?
F minus 32.
And did I get the parentheses in the same location as what we had written down before? Excellent. All right, so this is a formula that relates Fahrenheit and Celsius. If we were given Celsius, could we still use this formula to find Fahrenheit?
Yes.
Yes, we could. We just put it into the right location. So you do need to make sure you plug it into the right location. On this one, we are actually given Fahrenheit temperature, which is on the right-hand side. So we have 5/9, and it's 23 degrees minus 32. Your calculator will come in super handy on a problem like this. So we subtract first, right, inside the parentheses, and then multiply by the 5/9. What do you get for your temperature in degrees Celsius? -5. Is that possible? Sure. It just means it's below freezing. But you knew that already because it was 23 degrees, right? And a Fahrenheit temperature that's freezing is 32. So that makes sense as you're taking a look back at the problem. Okay, everybody good on this one? Conversions. All right, this one's going to require a bit more in terms of setting the problem up. Julia's soybean field is 3 meters longer than it is wide. To increase her production, she plans to increase both the length and the width by 2 meters. If the new field is 46 meters squared, larger than the old field, then what are the dimensions of the old field? There's a lot of stuff going on in this problem, don't you feel like? So what might be a good first step on a problem like this? Write down what you have. What else can you do? Draw a picture. So in relate, either what you've written down with a picture, some kind of an image of what's going on, because we are talking about a rectangular field. It's okay. Yeah. All right. So we've got the length and the width that are referenced in an original diagram, and it is rectangular. So we've got this kind of a shape. There's absolutely nothing about my picture that's meant to be drawn to scale, so please know that from the get-go. I'm not drawing things to scale. We're just getting us an image of what's going on. It says it's 3 meters longer than it is wide. So maybe you want to call it X or W for the width. And then what would the length be? L, but in reference to how they're, yeah, W plus 3, because it says it's 3 meters longer. So try not to introduce more variables than you really need in the problem. It doesn't hurt anything, it just makes it more complicated. So simplify where you can. All right, so this one is where it starts. It says it's 3 meters longer than it is wide. That's the first sentence. The second sentence says that she wants to increase her production. So she's going to increase both the length and the width by 2. Okay, so the field is going to get bigger. Let me change my color, it's going to get bigger like this, right? I don't know whether she's going to increase the length and the width on one side versus both sides, but it's a total of 2 meters on each dimension. So instead of it being W like it was before, what will our width be?
W plus 2.
Right, W plus 2. And instead of the length being W plus 3, what will the new length be? W plus 5. Okay, this does not work what I wanted to do. Let me try that one more time. Here. So our new length right here will be W plus 5. So everybody good so far? Okay, that's the second sentence. Now it says on the third sentence, if the new field is 46 meters larger than the old field, meters squared, then what are the dimensions of the old field? Okay, so what kind of quantity are we talking about once it said meters squared? Area. And so we have a formula on a previous page that I gave you that said that the area of a rectangle is what?
Length times width.
Length times width. So there are 2 areas in my picture, agreed? So area of the small white rectangle, and then there's the area of the larger yellow rectangle. I don't know where my W plus 2 went, where the 2 went. Let me put it back in. So we actually need to be careful that we're talking about the right area in the right location. It says the new field, right? So the new field, what's the area in terms of formula for the new field?
W plus 5 times W plus 2.
Good. So the area of the new field, and I'll write this down just to be real clear, the new area is W plus 5 times W plus 2. What's the area of the old field, or the original field? We'll say original.
W plus 3 times.
Okay, is everybody good with that? Okay, that looks good. Well done. And then it talks about how these are related. It says the new field is 46 square meters larger than the old field. So what would I have to do to make some sort of an equation that's solvable with this information as it relates to this 46 and so forth? What is it telling me to do?
Subtract 46 from the old one.
From the old one or from the new one?
Right,
The new one is bigger.
The new one is bigger.
yeah. See, oh, yeah.
So you could either add the 46 to the old one or subtract the 46 from the new one. And those are equivalent operations. But one way or another, there is going to be a 46 that's going to be added or subtracted. If you do the W plus 5, this is the new one, and the W plus 2, right? And you subtract 46, I'll put that one as our formula since that one was the first one mentioned. And it is going to be equal to the old field's area, W plus 3 times W. I'm just giving myself more room to work, so I'll move to a new screen. All right. There's all the same information I just had. There's one variable here, right? That's good news. Because if you have one variable, then you're able to solve for it. So if we had still had our L involved, we would have a problem at this point because we wouldn't be able to actually find a single quantity that would work. All right, so we worked a lot with expressions, what's on the left and what's on the right back in chapter P, multiplying, distributing these out, right? So on the left-hand side, somebody distribute out what you would get for me when you take W plus 5 times W plus 2. What are you going to get?
W squared plus 7W plus 10.
Right, and the 7W is coming from the inner and the outer terms being combined, right? Yeah, good. And then we still have a 16 here. Not 16, 46. That's what happens when I zoom in and zoom out too much, is my numbers start looking alike. What goes on the right-hand side?
W squared plus 3W.
Something very nice is about to happen. Does anybody see it?
W squared.
Yeah, the W squareds are going to go away. So if I subtract, if you will, W squared from both sides, right, they both add to 0, at least that component does. So that's very nice. So now I'm left with 7W plus 10 and minus 46. What's that?
Minus 36.
Minus 36. And on the right-hand side, I simply have 3W. What would you guys like to do next? All right, we going to move to 7? Sure. Minus 7W. So I have negative 36 on the left. What's on the right? Negative 4W. Don't forget the W. And then what? Divide by negative 4. So what's W? Yeah, it's positive, 9. And it's a good thing to check and make sure it makes sense, because if you did get a negative, you've got a mistake somewhere, right? Because this is representing the width of something. You can't have a negative width. Now, we found W equaled 9. We need to make sure we're answering the question that was actually asked. It's the question, my yellow is on top of it, but it says, what are the dimensions of the old field? Well, in terms of W's, what are the dimensions of the old field?
9 and 9 plus 3.
Right, well, okay, so in terms of W, they're the W and the W plus 3, right? Okay, so this white rectangle is what it's asking me for the information about. So we need to make sure that we get both the width and the length. And we already have the width, it's 9, and then the length will be 12, right? 9 plus the 3. So our answer to the question, we need to make sure we're answering it really, is that this is 9 feet by 3 feet, or not 3, sorry, 12 feet. 9 plus 3. Notice also there's units on there, right? It says feet. Or was it feet? Actually, it wasn't. It was meters, wasn't it? Whew. We need to fix that. Make sure you get yours fixed too. Meters. It was in meters. Those are different quantities, agreed? Yeah, a meter's almost 3 times, well, it's a little more than 3 times as big as a foot. We need to make sure we get the right one in there. Okay, so 9 meters by 12 meters. Okay, any questions on that one? There was a lot more going on that one than that problem about temperatures, right? Yeah, a lot more going on. All right, what's next? Let's see. Okay, this is a business type problem. All right, Brent lent his brother Bob some money. It's a really bad idea. Don't lend money to people. Give it to them or just say no. It's a bad plan. Okay. But Brent obviously did not learn that. So Brent lent his brother Bob some money at 8% simple interest. And he lent his sister Betty half as much at twice the interest rate. He's probably just going to lose all his money just saying that, okay? But assuming that he doesn't, it says both loans were for 1 year. And he actually earned some money back, $24, or at least he's supposed to earn back $24 in interest. And the question is, how much did he lend to each person? So there's probably not really a picture to be drawn here. But we do probably need to do what Andre suggested, like on the last one, where we need to figure out what we've got going on, right? He's lending money to different people, different amounts, but they're related amounts. He's lending them at different interest rates. And at the end of all of this, if they pay him back, he's going to earn $24. And he's probably going to have to remind them 10 times during the year that they still owe him money. But, you know, that's aside from the fact. And the question is, how much did he lend to each one? All right, so there's 2 people that are being involved in this situation. What are their names? Bob and Betty. There's also Brent, but he's the one giving the money. So we have Bob's amount, what's going on with Bob, and then we have an amount or a situation that's going on with Betty. They each get a certain amount of money, right? So we don't know how much either one of them gets from Brent, but they do get a specific quantity. So if we would let Bob have, so this is, let me put this in here. So this is the money borrowed. We don't know how much Bob gets to borrow, but let's call that X, okay? It's an unknown quantity. You can call it whatever letter you want. I chose X. How much will Betty get to borrow compared to Bob? Half X. So we're going to have either, you can use decimals or fractions, 0.5X or 1/2 X. That's how much money she gets to borrow compared to Bob. Half as much. But it also says that there's an interest rate situation, right, that's different. So here's our interest rate. So what interest rate is Bob borrowing at? 8%. I'm just going to write it as 8% for now. And it says that Betty's is twice the interest rate. So we actually know the interest rate for Betty too, don't we? Yeah, it's 16%. Apparently she is less reliable, so she's got a higher interest rate. 16%. And then we know that they're going to, or at least they're supposed to pay Brent back. And there is a formula that we have used already once that talks about interest rates. What is that formula? Back on the slide with all the formulas on it early, like page 1 of your stuff. Your interest rate formula. I equals PRT. Now, each of them have a P in the problem. That's what we listed first, the X and the 0.5X. That's the principal, right? We don't actually know how much it is. That's what we're looking for. The rates we actually do know. And then what does it say on time? It's 1 year, right? So we know T. Yes, Anna?
So in the end, you would get the same amount of money from both Bob and Betty.
He will on this one because one is half of the other one being doubled. Yes. Wouldn't have to in general on a different kind of problem, right? But we do on this one. You're right. Okay, so our total amount that Bob gets, so the total that Bob gets is supposed to be $24. And it's supposed to be the interest amount from each person, right? Okay, so how do we find the interest? In fact, I'm going to move this over here a little bit. How would we find the interest for each of these people? Sorry, I wanted to get my table moved around a little bit. Please continue.
I was just saying, you just plug in what you have into the equation.
Okay, into this equation right here, right?
Yes.
Okay, so for Bob, if I plug in the pieces that I have, his principal's X, his interest rate's 8%, and the time is 1. What would that be in terms of a variable quantity? What would it look like? This is Bob's interest. I'll write it underneath his column in a minute. His principal, we said, is 8x. His interest rate is 8%. What am I going to plug in for R? 0.08. And his time is 1 year. So in terms of a quantity, this is actually the same as having 0.08x, right? That's his interest value. Whatever the rate, whatever his thingy, whatever he borrowed, times 0.08. What about Betty? We'd calculate it the same way, right? We'd multiply the 0.5x times 16%. What's 16% as a decimal? 0.16 times the 1 year. What would we actually end up getting for her interest value? Yeah, and that's what Anna was noticing earlier on, is that this ends up being the same thing, right? Because of the halving and the doubling of the other quantities. All right, cool. So this is the interest that Bob gets. He gets 0.08, or not Bob, Brent. He gets 0.08 from Bob. He gets 0.08x from Betty. And this is supposed to equal what?
$24.
$24. So we should be able to figure out what amount he's letting each of them borrow. That is, we should be able to solve for x. All right, so what is 0.08x plus 0.08x? 0.16x equals 24, then what? by
5.16.
by 0.16. Divide by 0.16. What would you get for x? Did you get a value? Okay, well, what did you get? Okay, did anybody else get 150? Seeing the heads nodding, and 150 is what I have written down as well. So 150 is what x is, but again, let's make sure we answer the question asked. What did it say that we were actually asked for?
How much money did he lend to each person?
How much did he lend to each person? Okay, so how much did he lend to Bob? Yeah, Bob borrowed 150. How much did he lend to Betty? Yeah, half that. So she only borrowed 75. Okay, is everybody good on that problem? Makes sense? Sort of a little bit more complicated than that first one we did with the interest rate, but still an interest rate problem. All right, we've got Rita. Rita can process a batch of insurance claims in 4 hours working alone. Eduardo can process a batch of insurance claims in 2 hours working alone. How long would it take them to process a batch of claims if they worked together? Before we start working through the actual problem on this one, can you kind of ballpark what you think it might be? What's a reasonable number here? 2 hours? 3 hours? Be careful. They're working together.
1 hour.
It's got to be less than 2, right, Jonathan? Why?
Because Eduardo is the one who works works faster,
Yeah.
and he works one batch in 2 hours. So if he has someone helping him, then it would have to be under 2.
Do you guys follow that? Sort of when we're looking at the numbers, it's really easy to think that somehow it should be sort of an average of their 2 speeds. But it isn't, right? It should be faster than the fastest person because they're working together. So whatever answer we get, it better be less than 2 hours, or we've certainly got something that doesn't make sense. So our correct answer is going to have to be a number less than 2. All right, so take a look back at the formulas that you were given. Do you see a formula that seems like the kind of formula that would work here? What are we finding? What are we calculating?
Work.
We're calculating work. What was the formula that you had on that sheet for work?
Work is equal to rate times time.
Good. It's the same as, basically the same formula as the distance formula, right? Distance equals rate times time. Work equals rate times time. Okay, so rate and time are related quantities. Obviously, if the rate is given in miles per hour, then the time has to be in hours, that kind of stuff, okay? So those are related ideas. And in this case, we are talking about hours and how fast they can work. So let's talk about each person individually. We've got Rita. And we've got Eduardo. I didn't spell his name right. Let me try again. Okay. So these two folks, right, have a specific rate that they're given, and it's given on both of them in terms of how much they can accomplish in a specific amount of time in hours. Do you guys see that? So our time given in hours makes sense, which means that our rate given in terms of hours, what they can accomplish in a number of hours, also makes sense. So as we're taking a look at each of their amounts, we don't know the amount of time they're actually going to work, but we do know the rate at which they can accomplish getting one batch done. Look at Rita. How long does it take her to process a batch?
4 hours.
4 hours, right? So what could she do in 1 hour? How much of that batch? A quarter. So that's her rate. She can accomplish one batch in 4 hours. That's 1/4 times whatever amount of time she ends up working. She's going to accomplish 1/4 of a batch per hour. What would Eduardo's look like for his work equation?
1/2.
Yeah, 1/2, because he can accomplish half of the batch that he's working on in 1 hour. And again, we don't know how long he's going to end up working when he works with Rita. So that's the T is time, and that's the quantity we don't know. Okay, so now we're going to combine Rita and Eduardo's, whatever, rates, their work rates, so that they can actually work together. So when we're looking at this, we have We're still doing work equals rate times time. The work that's going to be accomplished here is they're going to finish the task, one batch of whatever, insurance claims is what it was, one batch. But we have two rate times because they work at different rates. One of them, Rita's, is 1/4 T, and the other one, Eduardo's, is 1/2 T. This is much like the problem over here where we added the 0.08x plus 0.08x, right? Each individual piece adds together to be the whole 24. Each individual rate time, each individual's work is going to add to be the whole work project completed 1, which is 100%. That's what's going on, or one batch. All right, so 1/4 T plus 1/2 T. What is that?
3/4.
That is 3/4 T. And if you don't want to use fractions on this, could you use decimals? You could, because 1/4 and 1/2 are very nice decimals to work with. And there's a 1. Now what we're going to do? Divide by 3/4 or 0.75, or you could multiply by 4/3. Okay, so I'm going to multiply by 4/3 just because I've got mine written in fractional form. And I'm not a fan, at least writing it out as dividing by fractions. It always looks funny to me. All right, so 3/4 and 4/3, of course, is going to cancel. What are we going to get for the time? T equals 4/3, which sounds kind of funny, 4/3 of an hour. So what would this be really in terms of numbers of hours? What does 4/3 of an hour look like? Oh, that's so much better to think of it that way, right? So 4/3 hour is correct. There's nothing wrong with it. And if you leave it like that, I'm not going to freak out. I don't even think my math level freak out. But it might ask you to say it in hours and minutes because that's sort of more like we really think about time. And this would be 1 hour, and it would be 20 minutes. So some of you might be looking at it and saying, well, where did you get the 20 minutes? And the way that you get that is if you were to divide 4 divided by 3, you'd get 1 and 1/3. The 1 is the 1 hour. The 1/3 is 1/3 of an hour. And how long is 1/3 of an hour? It's 20 minutes. So that's where that number is coming from. 20 minutes is 1/3 of an hour. You think of it in terms of a clock. All right, and one more example, I think, right? Yep, we've got a beverage company. A beverage producer makes 2 products. Orange drink containing 10% orange juice, and orange delight containing 50% orange juice. How many gallons of orange delight must be mixed with 300 gallons of orange drink to create a new product, Orangelicious, containing 40% orange juice? Could we really have not given them better names, right? I mean, really, they all have the word orange in them, just to make us really think through which one we're talking about, I guess. All right, so there's 2 different quantities or 2 different things going on. There's the quantity of each one of them, right? And then there's the percentage that each one of them actually is of orange juice as opposed to some other product, right? Sugar or water or whatever. So when we're creating this, I think a table would be helpful just to organize what in the world we have because we have a lot of information going on. All right, so there are 2 different kinds of products originally. There's orange drink. And there's, what was the second one? Orange delight. They're also just OD. You can't abbreviate even. You see what I'm saying? No abbreviation on those 2. Orange delight. And I mentioned that there's 2 different things that we have to consider. One is the percentage of orange juice. And then the other is the volume that we actually have, the number of gallons. Okay, so what is the percentage of orange juice in orange drink? 10%, which of course is the decimal point 10 or 0.1, just as a reminder. What is the percentage of orange juice in orange delight? 50%. And again, as a decimal, that's 0.5 or 0.50. And in a minute here, we're going to create a new thing called Orangelicious. I don't even know if I spelled it right. The Orangelicious is what percent concentration of orange juice? 40%. Okay, so looking at these, which are you going to need more of? The delight or the drink? How do you know? The higher concentration one. So did you say the orange delight? You're right. We're going to need more orange delight in our mixture than the orange drink because the concentration is 50% and our new concentration needs to be 40%. It's just closer to that quantity. Does that make sense? So whatever numbers we get, I better have more gallons of delight than drink. Okay, so just thinking through, like realistically, what does my answer have to look like when I'm done? That's what we're thinking through. All right, let's go back here and see what it said on quantities. It says, how many gallons of orange delight must be mixed with 300 gallons of orange drink? So we actually know one of them, right? We know the 300 gallons of orange drink. Cool. So this is 300 gallons. And we don't know the orange delight gallons. How much are we going to have after we mix them together of Orangelicious?
X plus
300 plus X or X plus 300. Good. Okay, so they're going to be added together, right? We've added two different things together. They add to their total amount. It's not like mixing dirt and water. It's two drinks. They just add, the volumes just add, okay? All right, cool. All right, so let's take a look at what happens when we're looking at this. If I have, we'll just look at the orange drink itself. If I have 10% orange juice and I have 300 gallons of the orange drink, how much of the orange drink in gallons is actually orange juice?
30 gallons.
30 gallons. How'd you get 30 gallons, Jonathan?
Just multiply the percentage of orange juice in the drink.
Right.
The volume.
Okay, did everybody understand what he's saying? He multiplied the percentage, that's the 10% times the total gallons. So if you want to think about creating sort of a third column over here, this is the gallons actually of the orange juice, like the actual number of gallons of orange juice, and we're getting that by multiplying. This is 0.1 or 0.10 times our 300. That's where it's coming from, and it's 30 gallons. There's 30 gallons of this quantity that's actually due to the fact that it's orange juice. So what would that look like in terms of an expression for the orange delight? I mean, I don't know the actual number yet, but what would it look like? Do you have an idea, Sydney?
5 times X.
Yeah, so we would have 0.5 times X here. And what would it look like for our mixture, this Orangelicious mixture? What would I need to do?
X plus 3 times 0.4.
So the amount, X plus 300 times 0.4. I'll put parentheses here just for fun. Alrighty. Yeah, okay. All right, so what would I do next?
Correct equation.
I need an equation. What would the equation look like? Do you have a proposal? Just are you talking, Jonathan?
You take the orange drink and the orange delight and they're one side, so 30 plus 0.5x, which will be adding them together, and then equals x plus 300 times 0.4.
Does everybody see where all that came from? I think it's easier to see because we created the table. I think that would have been very difficult to do without organizing the information to start. Very difficult. All right, so could we solve this equation now? Certainly can. There's only one variable, right? So we can do that. On the left-hand side, I can't simplify anything, but on the right-hand side, what can I do? Distribute. So I'm going to get 0.4x plus, what's 300 times 0.4? 120. And then what? Okay, so you want to subtract the 30 like this. All right, so what's 120 minus 30? 90. So this is 0.5x equals 0.4x plus 90. Now what?
Subtract the 0.4x by the
Good. Subtract the 0.4x. What is 0.5x minus 0.4x? 0.1x. And it still equals the 90. Now what?
Divide the 0.1 by 90.
Okay, so divide the 90 by 0.1 is what I think you meant. And so what is 90 divided by 0.1? 900. 900 what? What did we find? Gallons of Orange Delight. Now let's go back and actually see what the question asked us to find. It says how many gallons of Orange Delight must be mixed to create our new juice? And I think that's exactly what our answer was when we got to the end. We don't have to do any extra work at this point, right? Now let's check and make sure that it actually fits in what we said was true. Did we end up with more Orange Delight than orange drink? Yes. So that sort of checks off our reasonableness to this particular problem.